Back in 2010, Yahoo has acquired a small startup called Dapper. And that has been the base for Yahoo's R&D. Billions of products and select the right product for the right users. That's a technology that's been sold to Yahoo. Yahoo didn't have the technology at the time, and that's how we started. And I joined the company short time after the acquisition, while the startup was still in the offices of the startup. And I'm sure some people here know what I'm talking about in this situation. And about 2 years after we moved to our new shiny offices, the CEO of Yahoo changed, and Marissa Mayer basically came on board, and she decided to revolutionize the Yahoo properties. So Yahoo owns properties that serves billions of daily active users, such as the Yahoo homepage, the Yahoo Mail, Tumblr that was acquired since, and Yahoo Weather, and more Yahoo Finance. And basically, she changed. These properties used to look like a bunch of articles that were glued together by some manual editorial team. And Marissa decided to change all that and basically convert these properties into endless streams of content. Something like what you see today on Facebook, where you just scroll and scroll and scroll, and you can scroll forever, and more personalized stories are fetched from the backend, and they're specifically chosen for you based on what we know about you. And that basically opened up a new opportunity for advertising called native advertising. Native advertising is the kind of advertising that is non-intrusive. It's not like display banners popping and takeovers and all that kind of thing. It's basically advertising that is slotted between content usually. It can reside on any platform, and it's very native to the user. And basically, maybe it's luck, maybe it's the expertise that we had in the startup, maybe it's just the talent that we had in Tel Aviv, but we were the right people in the right place to basically start building this solution. And at the time, there were some miscommunications in the company, so multiple teams started to build it. And I was part of a 3-people team that started to build this product from zero, from line one. Actually, they rented offices. We didn't have office space in the office anymore. They rented us some office space outside of the office. And we're sitting there kind of like a startup within the company, and we started to build this product from zero, from nothing, okay? All the backend. And it wasn't ours at the time. Like I said, I mean, we had this Israeli chutzpah to start building a product. Nobody asked us to build it. Nobody said, hey, we need you to build this product for us. We just built it, okay? We built it. We glued some of the old Dapper infrastructure, and we took some new technology that was available since, and we glued and we hacked, and we did what we can, like some kind of like a 2-4 weeks hackathon. And at the end of these weeks, one of the founders of the startup at the time, the manager, the site lead at the time, took this. He flew to the US, to San Francisco. He set a meeting with the CEO, and he presented our solution. And it's really outrageous to do something like this, basically, in a company. 3 people are sitting, he takes it, and he presents it to the CEO, and the CEO says, that's amazing. I want you to build it for us. So that's how we started. And slowly but surely, we started to both hire and take and consume more and more of our site at the time, which was merely 15 people, something like that. And we slowly started to consume, and we stabilized around 7 engineers at the beginning, and we started to build this huge system at scale with the goal of reaching $100 million a year of basically yearly run rate. And that was our goal. A moderate goal for a team that used to do, I don't know, a few $1 million of run rate at a time. So that's what we're going to talk about a little bit today. Yes?
So what was the product?
Oh, that's a product. We'll talk about it. But that was just the exposition to tell you a little bit how this thing that we're going to talk about became. All this didn't happen, 10 years ago. It happened 3.5 years ago, something like that. And I was in a perfect position to basically tell this story because I was there from day one. And time passed. I became a manager in the team, and then I started to manage the group. And today I manage the entire group. We're about 30 people here in Tel Aviv. And we're still growing, we're hiring. So if anybody's interested, we definitely are. So let me talk a little bit about what Gemini-Native is. So like I was saying in the beginning, we're presenting ads that are non-intrusive and basically can be shown on any property. So on left we can see Yahoo movies, okay? These are ads, okay? This is an ad and this is an ad. You can see the images are very much like what you would expect. We try, some of our algorithms take the content into account and the context into account. This is Yahoo Mail, this is an ad. This is Yahoo homepage, this is an ad. This is a screenshot of an app, okay, of a native app. This is not a web browser or anything. This is a native app, Yahoo Sports app, okay? So as you can see, native ads are displayed everywhere today on all of Yahoo properties. Actually, today about 40% of our volume comes from syndication. So we're not only on Yahoo today, we're also syndicated. Actually, pretty recently, we started to onboard some test pilots with AOL. So we're running on TechCrunch homepage, some Gemini ads, some AOL articles, we run some Gemini ads. So if you see some native ads on these properties, it might have been us. Yeah.
The ads look like this automatically by an algorithm, or
that's a great question. So that's a great question. We don't control the visual aspects of the ads, okay? We basically do all the algos, we select the ads. I'll talk about it next slide, but the rendering, the actual rendering of the ads is up to the property, up to the publisher. It's not a widget. We just give JSON or raw data to the publisher, and he's the one to render it as the same way that he renders his usual content, and that's what makes it so native. Okay, so what is the responsibility of my team? What do we do? So monetization, okay, we're an advertising service. We do monetization of Yahoo properties and syndication properties. We're trying to maximize revenue, okay? We have a bunch of smart algorithms that are basically doing prediction and are trying to predict which ads will work well with which users and make us most money. So we're selecting which ads to show. We're calculating engagement prices. The prices are not constant. Each advertiser is willing to pay a different price. We're calculating all that in runtime. We're responsible for user experience, personalization and targeting, and of course for execution of business logic and marketplace control. Not to rattle into that, but just one example, just an anecdote. You know, this seems like a small topic, but you know that Yahoo, as part of syndication, we're doing the homepage stream of AT&T. Okay, and you know sometimes we get Verizon to advertise with us, so we get I don't know, Sprint to advertise with us. So apparently there's a penalty in the contract between Yahoo and AT&T if we show a competitive ad on their homepage. Imagine how humiliating it is for them. So there's tens of thousands of dollars of fine per impression. These are also the kind of rules that we have to evaluate and respect on our backend.
So is it also developed in your system, or you're
Yeah.
using a third party?
No, it's all on our system. Let's talk a little bit about numbers because this is talk about scale. So let me introduce you to our scale a little bit. So we're getting more than 2.5 billion impressions a day. Okay, that's the kind of scale that we're looking at. The peak load in the system, and this is really peak load. It's not like an emergency load, some servers are down or whatever. We are ready to get 160,000 queries per second across our network and across our system. In order to do that, we maintain more than 2,000 serving hosts around the world. And I'll talk about that in a minute. We have millions of ads in our inventory. So every time we get an impression, when I said we need to select the best ad, it's not just of a few ads, it's out of millions of ads. And not only we do it 160,000 times a second. Book to serve. So, you know, when an advertiser makes a change to a property of his campaign, or, you know, he changes his bid, he changes his title, we can guarantee that it will make it to all of our 2,119 servers around the world in 10 seconds. We have dozens of online experiments run in parallel, even right now, and millions of clicks a day. Okay, so that's the scale of the system that we're talking about. Remember, we started from a few lines of code 3.5 years ago, and that's the scale that we're doing today. Today, I can't get into very specific numbers, but the revenue that we're making is in the run rates of billions of dollars a year, and is reported every quarter to Yahoo's investors as part of the investor calls, the quarterly investor call, because the scale and the revenue that we're making is so significant to the company that it's actually reported first class in the report.
The whole market of advertising is billions, tens of billions.
Is what? Sorry?
The whole market of display advertising.
This is not counted as display advertising, not also in the reporting of Yahoo. And yes, this is the rate that we're talking about.
No, your numbers are big.
What?
Your numbers are too big. Because the whole market of internet advertising.
Yeah.
You said hundreds of billions. You mean?
No, not hundreds of billions. I said it's billion. The run rate is $1 billion run rate. That's what I said.
He thought they're hundreds.
I mean, the actual number is hundreds, many hundreds of millions of dollars
Millions, not
a year.
billions.
No, okay, so maybe I misspoke. The run rate is in billions of dollars, but the numbers, that's the run rate. But the actual numbers are hundreds, many hundreds of millions a year. A year. Okay. Also a quarter. If you divide it by 4, then also a quarter. Okay. So
How does this compare to some of the other major ad serving systems?
So the leading player today in native world is Facebook. Google doesn't have a real step there. They're very strong in search. They're number one by far in search. But as far as native, Facebook is the number one by far. We have Taboola and Outbrain are not doing exactly the same thing. They don't have their own. Unlike Facebook and us, they don't own the publisher. We own the publisher, right? We own our properties, so it's not apples to apples.
Are you showing only like banners or banners with text? It's like RTB system or?
We do have RTB. It's not banners. Yeah, I'll repeat the question. So he asked do we show banners with text or image, or how does it work, and are we open to RTB? So it's not banners per se. It's not widgets. We return data to the client, and they basically render it as part of their content stream. Okay, so we do not show banner, and it's up to the property to decide which assets to use. They have a title and description and an image and a high quality image and sometimes video, and it's up to the client's rendering capabilities to render it to be native. So if you are in a stream, if let's say the property is a video stream, okay? So it will render the ad. If it has a video ad, it will render the video ad, right?
It will be calculated like CPC or CPU, CPM?
We support all of this. We support CPC, CPV, conversion, everything.
CPA as well.
On engagement, yes. Also on installation, yeah. Okay.
So compared to Facebook, how much larger are they?
I don't know how larger they are, but I think they're in at least an order of magnitude. They're huge. Okay, let's talk a little bit about, we talked about the scale and the host. Let's talk a little bit about how it's set up across the world. So Yahoo owns and operates its own data centers. It's not like we go with Amazon and EC2 and we're willing to pay more money. Immediately we have a virtual host and we can serve. It doesn't work like this. Actually, Yahoo owns multiple data centers around the world, and Gemini as a system is launched over a leading marketplace across the world. Today we basically own and operate hosts in 6 data centers around the world, 3 in the US, both coast and in the center, 1 in Europe, and 2 in Asia, to serve our Asian market. But actually, the markets are much larger than this. For example, we launch in Australia, we launch in Brazil, we launch in Canada. So, this gives us pretty good coverage around the world. There was a question somewhere? No?
Is that better than if you use some cloud?
I guess there's benefits and there's some cons. The pros are that you own your own destiny. You want more gear, you just buy the gear, and when you run at this scale, so economy of scale basically yields that you operate it, you control it. It can save some yields. But recently, Yahoo has started to consider actually the migration to a hosted solution. That hasn't materialized yet. But that's how it works.
When you have the peaks, so you need to buy the equipment for the peaks.
Right. We have equipment for everything. That's right. So it can be underutilized at times. You're right. You're right. Yes.
Did you make a conscious decision to choose data centers, or was that a given when you started?
So when we started 3.5 years ago, that was across Yahoo decisions. It's owned and operated, and we just went with the flow. You can think about it some ways. We have up and running and operating hosts that are there just for peaks or just for an emergency in case one of the other data centers go down. So there is some waste in that sense, yes.
So you have hot standbys essentially?
Yes. Yeah.
And they're in the same data centers?
Yes.
And these are Yahoo operated data centers?
That's right. So if, for example, the Nebraska data center goes down, then the traffic is split between the two hosts. And when we do capacity planning, we always take these things into account. But one of the biggest cons of this approach is that if, for example, we know that there's going to be a peak, it's Christmas time, or there's more users going into Yahoo or anything like that, it's not like a click of a button. We need to order gear, it will be there in a month, and it's being shipped and it's being installed, and these things take time. So we have to be very conscious about capacity and how we manage it, and I'll talk about it towards the end of this talk. Okay, before I go to the next slide, I want to move to this phase of this talk, and before that, I'm going to give a short exposition. So, I'm here to talk about how do we scale $1 billion system, and we all seen the scale, and the scale is big. I can talk about a lot of topics, but I chose 3 topics to talk about today. So we're going to talk about online. How is the hardware set up? How do we do launches? How do we do deployments? And how do we track it all? It's not perfect, it's not just dev, right? It's dev and DevOps, and how do we manage it across the team and all that. So you can think about it as a wider topic. That's what we start with. Then we'll talk about how did we evolve the architecture of an offline pipeline that is revenue critical and can have no downtime. So we'll talk about some of the architectural decisions that we've made. And then at the end, we'll talk about some online optimizations that we've made to the system to basically be able to scale. So we'll start with the building block of the serving system. I need to give you some background of how the serving system is built. So the serving system is built on top of Vespa. Vespa is a search engine, an app container that is built in Yahoo. It's built by a team in Norway. It's similar to some open source products that you may know, like Elasticsearch, for example. But only that this product, unlike open source, is being developed by a team of specialists in Norway, and these guys are eager to get a request and implement them immediately. Whenever we need some platform enhancements, these guys are our go-to guys. A typical setup of this platform is considered of 3 components. So one component is a QRS, one component is the searcher, and the third component I'll talk about in a minute. The QRS is the query server. It runs our application. The application is written in Java, and that's what it's doing. It's running the application. All the business logic runs there, and it compiles a query to the search engine core, which runs on the searcher. And the third host is the config server. The config server is responsible for the configuration of the cluster, for launching of new versions of the code, and also for feeding the searcher with new as updates, etc. QRS and searchers are set as a logical process on a single physical box. As you can see, they're grouped together, and we can have as many of them as we want. Once you group multiple hosts like this together, you get what we call a cluster. Okay, so each one of them is a working unit, and you can group a lot of them. Usually in our production host, we have something like 170 grouped together, and they form a cluster, and the entire cluster has one config server. Okay, so it's responsible for deployments, it's responsible for identifying bad nodes, etc., etc. And all these hosts on the other side are basically exposed to a load balancer, which distributes the load on the serving time. Okay. The way the application is set up, and the way we set it up in the data centers, is that each data center has at least 4 clusters. Some have 5, some have more. And the reason why we did it is because this is the deployment unit. So whenever we do a deployment, we can take out of rotation an entire cluster, and the system operates normally. Okay? So we take it out, we do maintenance, we bring it up. There is no service impact anywhere. Okay, nobody needs to feel anything. And also, we talked about it when we do capacity planning. We always take that headroom into account in the other clusters. So we always have about 33% headroom, so we can take a cluster down for maintenance. Okay, and that's something that we routinely do as part of the launch velocity pipeline, as part of the maintenance that we do. That's something that we regularly do. Okay, the release process for this kind of a system that serves so many users, and downtime of minutes can be tens of thousands of dollars cost of this downtime. So when we're launching new code, it basically goes through a full launch velocity cycle with unit testing and functional testing, and these guys have pretty good coverage of the tests. But we have one additional phase which you don't find in any typical launch velocity pipeline, and that's stress testing. Okay, so on every version that is compiled and is ready to go to production, we're running an automated stress test. The way we run the automated stress test is we basically implemented the ability to replay all traffic. So we can go to all serving logs, let's say from yesterday, the day before yesterday, from last week, or even from last year. We can take these logs, we can put them into a feeding mechanism, and it will start making calls very, very rapidly to the production hosts, or to any host that we specify. So for the launch velocity, we have staging environments with hosts with specs exactly the same as they are in production, set up in clusters, and we basically start calling these guys, bombarding them with calls, as much as they can take. Okay? Now we have our SLA. Our SLA today is 60 milliseconds, 95 percentile, and 80 milliseconds, 99 percentile. That's just about. And we basically make sure that these SLAs are maintained by both versions and that there's no degradation between the versions. So we test old code that is currently running in production against new code, which is the running candidate, and then we run the same profile, the same index. Everything is the same boxes, just not the same code, and we check for the aggregation of performance. Okay, and these are also plotted across, around graphs, so we can basically go back in time and see what was the performance on each release. Yes?
You have a full mirror infrastructure for testing?
A full mirror? What do you mean?
Sounds like this would require essentially a mirror infrastructure for testing, right? Because while you're playing, right, your production infrastructure still needs to take requests.
Right. So
what's
like I said, we have a staging infrastructure, which is smaller than the production infrastructure, but the specs of the gear are identical. And if you remember what I showed here, so we have the working unit, right? So we basically know the capacity that each working unit can take, right? Each node can take. So we don't need a full replica of production. We only need to replicate a few nodes and test them, and then we can pretty much multiply the numbers and get to our overall capacity. Okay. Once the version has been ready to serve, is deemed ready to serve, it's still not deployed everywhere to all of our 2,000 nodes at once in a click of a button. If we used to do that, we don't do that. Instead, we do something that's called a phased launched. How do we do it? So basically, we took all of our gear in production. It's all the same gear, but we basically split it into stages. Okay? So we have 1% of the gear that is called beta, 5%, 25%, and 100%. And basically, together, they form our stages of the release. So as soon as the code is ready, it automatically deploys to beta, okay, to 1% of the traffic. It runs there for a few hours, and then we look at business metrics, because some business metrics, marketplace behavior, once you launch a feature, some of them change user behavior, some of them cause tiny changes in the way the ads are shown or the algo or whatever, and you don't want to just introduce them. You basically want to ease them into the market and to see how they perform. So the code is launched to 1%. We look at business metrics. Then the code goes to 5%. We look at business metric. Then the code goes to 25%. We look at business metric, and then it's deployed everywhere. And on every stage, we basically look against the bigger stages, right? So if I have code now incubating in 5%, I compare its performance against the rest of the traffic. Now, this process, what makes it more complex is because we iterate very quickly and we have sometimes one launch a day. So basically, we call it like a caterpillar, because basically you can have a version of code here, another version of code here, another version of code here, and another version of code here. And they all routinely progress and move from one stage to the other and from one stage to the other and being evaluated. Yes?
Which tools do you use? Because it seems that you manage it manually, or do you have like an automatic?
Yeah, I'll talk about it next slide, I think.
Okay, and how much time does it take to get to 100%?
It can take anywhere between, if we follow the entire process, so since the code is ready, it can take something like 2 days, 2.5 days.
How do you handle cases where, let's say, you start to release something and it goes through the pipeline, and then you release something else, and then you realize you have a problem with the one you released before? Stop everything and roll back to the latest stable one?
So it depends on the problem. Usually, the way we develop code in my team, everything is protected by feature flag. So usually we can, if it's a feature that we can turn off, if it's not an emergency, the code will go to production and we'll launch a fix in the next version. But if it's something catastrophic, let's say that we launch something and it causes some memory leak that we didn't find, or it actually degrades metrics and we don't know why, then yes, we go back, we basically eliminate this, we cherry pick the commits that went into this version out of the other versions, and the pipeline continues. And it happens from time to time, unfortunately.
Stable version to propagate again through the pipeline, or
No. Once a version dim state, we can launch it anytime. Okay. So like I said, we can have 4 versions running for production in any given time, and it can actually cause some confusion. So, I talked about it, I think. Yes. Okay. So, as I said, we're collecting business metrics, and the business metrics we're collecting are things like CPM, CPC, price, engagement prices, all the business metrics that we care about. And in order to collect these metrics, we build a state-of-the-art, log aggregation system that we call it Cerebro. It's built on top of Splunk, Hive, and Storm, and it's a near real-time event processing pipeline to basically allow us to iterate as fast as we want. Because like you said, getting evaluated across the system, if we have a one-time-a-day batch job that gives us a report, will take weeks or a week to launch a code. So instead, we build a system where the time passes between the time that user is doing a click on one of our ads or the user impresses an ad on one of the properties anywhere in the world. In under a minute, that event is already logged, aggregated, and displayed for analysis. So we have almost 0 delay in the time that takes us to basically have data for analysis. And that's why sign-off of a version on one stage can take as little as a few hours, because the data is immediately available for us. Somebody else? Yeah.
Could you explain us how do you do log aggregation? Because Splunk does log aggregation by itself.
Who?
Splunk.
Yeah.
It's a log management system. So how would Storm Hive?
So I wasn't planning to get into it, but in a few words. So basically, we have the events are flowing in, right, from the properties into a queue. Okay?
Storm.
What?
Probably. Storm.
No, into a message queue. And then we have Storm pulling from this queue continuously and basically aggregating data into chunks, because the data is too granular to put it in Splunk. Splunk will crash. You need a very big Splunk cluster in order to be able to handle all this data. So we're doing some aggregations in the Storm level already, and then we put this into Splunk and then doing the actual reporting aggregations in Splunk. Okay? This is the UI in Splunk. I can't show real data apparently because it's proprietary data, but this is how the window looks like when we pull the report. Okay, so we can pull on dates and times and on publishers and colo names. Colo is basically data center, and on cluster and other things that are proprietary, and basically get the data. And at the end, there's all the raw data, but there's also a small table that says, are we clear to move ahead based on the predefined thresholds. A byproduct, without numbers, this is one of the graphs that we can see. So this is basically a comparison of one metric for each cluster. Okay? A byproduct of this system is something very interesting that maybe I'll talk about in another meetup, which is a bucket analyzation system, which gives us, I said at the beginning that we have dozens of experience running on real time and on any given time and analyzing them on near real time pipeline, basically minutes since you launch the bucket, you can already derive metrics, is also something very strong. And that's one of the products. This is, for example, one of the dashboards. These are buckets that were running at the time. I had to cut it at some point. You see, there's too many. This is a pie chart of the buckets. And basically, you can see revenue by bucket, and you can see the actual comparison of the buckets. And this is all coming real time as well as part of this system that is being used for other things as well. Which tag is deployed to where and when? Oh yeah, sorry.
Some consideration why to build it by yourself and not just pick maybe ELK or other kind of ready-made open source.
We already had Splunk used for other things in our system, in our team. We already had Storm used for other things in the team, and we also already had them connected. So the overhead of building it was not that big, and we knew the technologies and everything. So we built it in a couple of weeks, really. Okay, so which tag is deployed to where and when? I said, we have tags flying everywhere on different clusters, on different traffic shares. It's hard to keep track, and for that we actually built another system, which is keeping track for us of which tag is where, when it was deployed, what is being done, and not only for that, but also for other changes. I mean, DevOps are making change all the time to the system. They take down a cluster for maintenance, they take down a host to check it. They do that, and we want to keep track of what's happening all the time. So here you can see basically a table that demonstrates which tag is deployed to each cluster. Right now, everything is aligned. You can see beta, which we talked about. You can see prod, data center, which cluster we're talking about. And of course, this list goes on and on. And here you can see traffic switch build, which basically tells you when the deployment happened. This is only for non-US data centers, but this tells you on a timeline when the deployment happened for each cluster. And when you click on it, that you don't see here, but when you click on it, then it opens you the full log and all the information, what was launched and why and all that. Here you can see another view of actually the log. So every time that there's some build or some change done by the launch velocity pipeline or manually by one of our DevOps guys, so it's being logged to a centralized place, okay? And we actually opened it up as an API for other Yahoo teams, so they also use it. And here you can see that Tariq and Yuda basically stop traffic to one cluster in TP2. And here you can see that Screwdriver headless user, which is our launch velocity headless user, deployed these tags to some other calls 2 days earlier. And I'll say in a comment that if you're interested, then Yahoo recently opened some of this infrastructure open source. I put a link here in the presentation. It's called Screwdriver, and it's built on top of Jenkins. It's pretty cool. So just as a side note, if you're interested, then take a look. It's very nice. Okay. Moving on. So basically, that was a little bit of mix of DevOps and how do we manage and how do we do the releases and all that. Let's move now to something completely different, and that's the budget pipeline. Okay, so I said at the beginning we have 3 topics. That's the second. I'll start by giving some background. So in advertising, advertisers basically define budgets. Okay, that's what we do. We make money. They define budget and bid, and they get billed based on interactions. So if you're an advertiser and define $1,000 budget and a $1 bid, and in a perfect world, every time there's a click, then $1 is subtracted from your budget. Okay. Now, the responsibility of subtracting the price of the interaction from the advertiser budget is on the advertising system, on us. So we keep track of everybody's budget, where they are in respective to the overall budget, and when they get to 0, then it's our responsibility to stop showing them because they have no more budget to pay for interactions. And if we show them, instead of showing somebody else that could have paid for their interactions, they're basically getting free clicks, free interactions, while we could have made the money from another advertiser. That's called over delivery or overspend, and it's very bad. The opposite of that is under delivery, which happens when an advertiser actually has a budget and is willing to spend, but we don't show him. We don't realize that he has a budget. There's some miscommunication between the systems, and we don't show an advertiser that is willing to spend. That is called under delivery or underspend. Let me tell you a short anecdote. Yeah.
You said that your target is to maximize the revenue.
Yeah.
And do you use and utilize insights from test A and B of
A/B testing? Of course, yeah.
in your algorithms?
Yeah. So advertisers can upload any number of creatives, and we automatically A/B test between their variations. And this quarter, we're actually working on a feature to automatically generate their variations and to A/B test between different variations of the same ads. Yeah, to do it for them. Let me tell you a short anecdote about what we're seeing here and about overspend in general. So this is a screenshot that I took from a revenue dashboard in May. This is revenue. Of course, I had to erase the numbers, but believe me, this is the normal trend, and this is some anomaly. And basically, what you see here is what happens when the system goes to an overspend mode. So in this situation, one of the components of the system, not in our system but somewhere upstream, didn't transmit the events. Okay. As a result, we let advertisers spend as much as they please, as if there's no budget limitation. Okay. And as you can see, that's what happened. This right here is something like $200,000 in 1 hour. Okay, of unregulated spend. Okay. Besides looking very bad for the advertisers and having to refund them $200,000, this is also very. This means that we didn't show other ads that could have, we could have made real money from. So this is why I'm saying this is very bad. Let's talk a little bit about architecture. Let's dive in a little bit. So I told you at the beginning this very moving story about how the system came to be. And at the beginning, we knew from the beginning that we need to build a budget management pipeline. Budget management, the cloud over there, was already it existed before us. It was, it was managing the budget for some legacy systems as well. And we had to coordinate with it. It already had the capabilities of managing the budget and to send the updates when the budget has been depleted or not. And we needed to interact with it basically to get the updates and send it all the way to all of our serving clusters. I said 6 data centers, I only plotted 3. So the way it was built is like this. This guy is producing something like 300,000 messages every 5 minutes, something like that, okay? It's a lot of updates for all of our campaigns. And it saves them to an edge-based table we call BudgetDB. It also, on real time, it sends them to 2 queues, red queue and blue queue, which are completely separated, 2 different sides of the US. Okay, 2 data centers completely separated. Then we have 2 storm pipelines, 2 storm topologies, reading from these queues, eliminating some redundant data, some messages that are not meant for us, but meant for other legacy systems, meant for disabled ads, etc. And basically, these guys also running on the same data centers, 2 sides of the US, save the results into a serving DB, and at the same time, they also send an update to boxes, to Tomcat boxes, residing on each individual data center, okay, with the respective updates. Okay, the reason why we have this additional op is because we wanted to aggregate. There's a lot of updates coming in all the time. We wanted to aggregate 5 seconds or a certain number of updates together and send them in a batch for performance reasons. And these are the actual serving clusters, which are getting every 5 seconds or every certain number of events, they get the updates from the budget updater. That was the pipeline. And it was very important, as you saw, to keep the latency, the end-to-end latency from the time that these guys know that the budget is out to the time that all of our 2,000 servers know that the budget is out. Very, very minimal. Today, we keep it under 30 seconds, okay, end-to-end, for all these 300,000 updates. So this was the pipeline, and we launched, it worked, but it was very, very fragile. One of the reasons why it was very, very fragile is because Storm, which I'm sure that many of you know of, is relatively new, and Yahoo and my team were relatively early adopters of the technology. So we built it early 2013. So there were some stability issues with Storm, also with the internal clusters that were set up by Yahoo. Remember, we own our own data centers and all that, so we also own our own Storm clusters, and they were unstable. Okay, and they used to crash for I don't know 20, 30 minutes, and then somebody from DevOps would come, bring it back up, and everything is normal. Although in these 20, 30 minutes, if we haven't detected it on time, so we basically missed a lot of updates. And as you can see, $200,000 an hour, it's not that good. So we basically built these 2 parallel pipelines, and we could switch between them, but it still required manual intervention. And switching between them still took precious time, and we ended up losing money. Okay, so there was a downtime. we were thinking, how can we improve this pipeline? What can we do to improve it relatively simply? And we ended up going with the proven design of basically moving from a hot-warm approach, where one cluster is warm, one pipeline is warm, and the other one is publishing, to a design where both of them are publishing all the time together at the same time. Okay? So they're both publishing at the same time. Now, there's basically, if one of them falls, then we go back to this. So no problem, automatically. So as long as one of them is up, we're golden. It's just, the problem is that now we already had pretty high volume of updates going through this pipeline, and we had to keep very low SLA. Now, we have double the updates, right? Because both pipelines are sending all updates, and now it's double. So what we ended up doing was a simple deduping solution. We had a budget management system stamp each message that it sends before it forks them to both pipelines with an ID of with an ID. The ID was basically the generation timestamp in milliseconds. And then when we were getting the messages in here and in here, we had a small queue, right? We said everything comes in batches of 5 seconds. So within these 5 seconds, we used to dedupe the messages. So if we get two identical messages, two identical timestamps for the same entity, campaign or advertiser, with the same ID, we would dedupe it. We would discard one of them. And later on, we even further improved it, because we said, if we already have the timestamp, why even sending it in the first place? Why not sending the newest one? What if you get two, it's not unusual to get an update second after second after second after second. Why sending all of them? Why not just using the newest one? And that basically reduced the volume that we had to index and process by a lot. Okay? Now, this was great. Now, the pipeline was not that fragile anymore. But, every time there was some spike in revenue, every time somebody suspected something, they used to call us, sometimes in the middle of the night, sometimes in the middle of dinner, and we didn't like it. So we ended up building some monitoring on top of that. We started by, we said that overspend is bad. And we thought of a very simple solution to prevent overspend. By basically what happens when there's overspend, the budgeting system tells us there's no budget to be spent anymore, but the serving system is serving the ad. Okay? That's overspend. So implicitly, what you don't see here is the feedback loop, right? Because budget management gets all the interactions that happens on the properties on real time. So think about it, the budget management knows everything it needs to know. It knows that it told us, it basically said stop serving, but it sees that interactions are still coming in. So what is the most trivial thing to do? Just send the freaking message again, right? So that's what it's doing. It's sending something that's called repeat. And if it sends us a message and says stop serving, and it still sees the ad serving, it sends a repeat. And if in a minute it sees that we're still serving, it says another repeat and another repeat and another repeat until the ad stops serving. And actually these repeat messages are something that we monitor, and we look at them like your bad cholesterol at your bloodstream. We look at it as something that is bad in the system, and we see they spike, and if we see there's too many of them, that's a good indicator that something is going on in the system. But we also talk about underspend, and underspend is not detected by this, because an ad cannot serve by a number of reasons. It cannot serve because it has too low bid, because it has targeting, any reason. So we built this system, the budget audit. Budget audit basically connects between the budget DB, which is the source of truth for everything budget, and our end cluster. Each one of our 32 production clusters is connected to it, and it periodically, every 30 minutes, it connects to all the 7 clusters to the budget DB, and it does a join. And it basically looks to see that everything is identical in both ends. But it's not only doing that. If it finds a discrepancy, if it finds that something is different, then it also sends its own message. It generates a fake message and sends it to the queues, so it will be processed by the pipeline. Okay, and of course, all these are monitored, and there's alerts and emails and phone calls and you name it. But even this did not satisfy us, because we also talked about the SLA. We need things to flow, not only to flow, but we need them to flow quickly. We want to identify bottlenecks as they appear. If, for example, there's a bad node or a bad cluster or something going on here, I want to know about it, not after 30 minutes when I run the audit. I want to know about it immediately. So for that, we built another system called the budget monitor. Basically what it's doing is constantly sending what we call isotopes or fake messages to the pipeline for ads that are not really serving but are indexed. And it also queries the production clusters, each one of the production clusters, to see when was the latest update for them. And then it can compute the round trip time of the system. Okay? By computing the round trip time, we can constantly monitor how much time does it take for a message, for an update to flow end-to-end in the system. And also, because we monitor each flow, each one of these errors, each one of these things, we check that they're flowing. And by doing that, we can actually say that a single line is broken, that one cluster is not getting updates, and take care of it immediately, usually within less than 5 minutes for detection and remediation. Yes?
Why do you monitor the round trip?
Sorry?
Why do you monitor the round trip time?
Because we said that this needs to work quickly. If it doesn't work quickly, then we're overspending on other spending. So time is money in this case. And if you sit idle for 5 minutes and you let things to run stale, then you can see the spike that I showed before and what happens when advertisers are unregulated. All right. Now, back to this, without all the monitoring, the pipeline that worked. And it worked for us for 1.5 years with no issues. But just look at this. It looks complex. It looks dirty. It looks like there's too many hops. And we built this to work in scale, but eventually we decided that Storm here was an overkill. I mean, the overall workload by Storm here did not justify the overhead of maintaining Storm. And also the hop here was too much, so we ended up simplifying it a lot, and we launched it on 2016. We launched the new budget pipeline. It's called Budget Beast, where the actual logic of the budget pipeline resides in each individual serving cluster. Okay, so now it's distributed. Each cluster takes care of its own budget management, and it consumes directly from the queues. Okay, and now we have a fully distributed system. If one box is down, then we only need to take down the specific cluster, and it not only simplified the system by a lot, it also saved 2 hops along the pipeline. It improved the speed of the updates going through the pipeline, and this has been running for 1 year with no issues, and we like it. What? No, the monitoring is still there. I just removed them. It's the same, right? It's external to the system, so they're running the same thing.
So you're not serving DB from previous version?
Yeah, we don't need it anymore. We just query BudgetDB directly.
Sorry, I forgot, what is the difference between the red and blue queues?
It's running on 2 separate data centers. So if one data center burns or they have an outage or power issue, so the other one is flowing. Yeah.
It may be 3 queues.
What, sorry?
4 queues.
Yeah, it can be any number of them, but usually we consider 2 to be good. If it's good enough for the airline industry, then it's good for us.
How big is the ActiveMQ cluster?
The what?
The ActiveMQ cluster, how big is it?
Actually, I don't know. This is managed by some other group in Yahoo in the cloud, and they add capacity as they see fit, but I have no visibility to other usages. It's not privately owned by us.
Sorry, you just get certain resources, right?
Yeah, we get resources, yeah. We provision with them, but they own the capacity and the host and everything.
So you get a few 100,000 messages per second? Or?
No, a few 100,000 messages per 5 minutes. Yeah. It's something like 1,000 messages a second. It's not that much. That's one of the reasons why we had no problem simplifying it.
Have you considered Kafka or something more?
Yeah, I mean, Kafka is nice, but that's just instead of the queue. I mean, today they're using ActiveMQ implementation. They can use another queue implementation.
So why did you have 2 DBs in the first place? Serving and budget?
Yeah, it was just for completion. We had this DB anyway. We're using it, for a centralized place for all the data that is going into the index. But the simplification of this basically yielded that we don't need it anymore. So budget data is not served in this DB anymore.
So you just an updater you connected with serving cluster updater.
Yeah, each.
Because you have updater and
Yeah.
config updater.
Yeah, and the budget updater used to basically group updates together, right? It used to batch them together. That's part of Budget Beast now. So it's running on each cluster individually.
But it's kind of separate component of the cluster, separate.
Yeah, it's still doing that. This is a logical process, so it's just residing on the same node as the cluster config server, but it's still separate, right? It still gives you an abstraction between the update itself and the cluster, and you still dedupe and you do everything that they said, just you do it on each cluster individually. So instead of having a centralized system, now it's distributed.
But
Yes?
do you still have a shared database between all clusters? Or each one
No.
has its own database?
Each one of them has like I said, each box actually has a search node, right? We said there's QRS and a searcher. All the data, the database, is in the searcher in each serving box 2,000 times.
They should be identical.
They should be identical, and we take care of it by the audit process, right? So the audit process goes, and we make sure that they're all compared to a single source of truth. Yes?
The budget beast doesn't need to communicate with the other beasts.
No, each one for itself. They're all running exactly the same code, and they're reading from the same source. If there's a discrepancy, it will be identified by the audit process and will be corrected, right? Yes? Okay. All right. Moving on to the last topic. So we talked about, how it is to operate and, to manage and deploy and all that. We talked about an example of an offline pipeline that needs to be resilient. And now let's talk a little bit about how did we scale one aspect of our online serving system. So the biggest factor when it comes to the online serving system are naturally memory. Okay, we have hosts, the hosts have memory, and as the index size grows, as we get more and more advertisers and the product grows over time, then they use more and more memory. The entire index is stored in memory for speed, and they consume more memory. The other factor is CPU. Okay, when we run in runtime, when we're doing prediction and we're doing everything that we do, all the computations that we do in runtime that I talked about at the beginning, and we do it over and over and over it again, then the CPU usage tends to grow, especially as the number of ads grows, because more ads means that we need to rank and test and to see targeting on each individual ad. So this is one factor of higher CPU, and the second one is the supply, or basically number of calls that we're getting, because as you're getting more and more calls, then naturally, your hosts are working harder. Here we can see two graphs. This is last 6 months of a supply trend. So basically, this is the number of calls that we're getting, and you can see the trend. The trend is clearly growing. And here you can see the trend of the demand, and there was some drop here, but there's an increase. So also the overall trend of the demand side of the number of ads in the index is also increasing. So scale is a big problem for a system like ours, especially that we cannot just ask for more gear when there's a sudden spike. We have to plan accordingly. Yeah.
Go back. So here you see this. Is this a seasonal trend, or is this
You
does
know,
that make sense?
I mean, yeah, we definitely see some seasonality, absolutely. But also sometimes sales do a better job in selling the ads, and sometimes they don't. So yes, there is some seasonality, but there's also some things that are not seasonal. Okay, so the way we handle the memory issue is by just buying hosts that can support a lot of memory. Today we have each one of our 2,119 hosts has a spec of 48 cores and 128 gigabytes. That's the standard way that we get it from the factory, and we can expand it to gigabytes of memory if we wanted to. And memory is cheap, so one way to do it is just to scale by memory. Today we have 5x headroom for memory perspective. Yeah.
Run Java, right?
Yeah. Run Java and C++. The core is written in C++, and the application is written in Java.
So how do you use the 128 gig in Java?
Because we need to store all the index.
So basically, the garbage collector memory allocation in Java is quite limited. So
Yeah.
if you give it 108 to one process, it probably won't be used.
Yeah, the Java application is not taking that much. It's the actual index that is managed by the C++ process that is stored in memory.
5x memory available.
Yeah. Yeah, we actually had so much memory available that we started to use something that, I don't know if you usually see it, but it's called tempfs as part of Unix. Once you, what? RAM disk, yeah, exactly. Once you get above a certain threshold of memory, then you get tempfs, and we're actually using it for some usages, which is nice. Supply growth. So when we look at this more users coming to Yahoo, which is always a good thing, or if we expand to syndication, these are usually more strategic things. And let's say that when Yahoo acquired Tumblr, for example, and they have a lot of users. So it's something that we knew that in 2 months we're going to do the integration. We had enough time to buy more gear. These things are usually slower trends. Demand growth on the other side, on the other end, we have self-service products. People can come in at any time and bring in their demand and bring in their ads and now serve my ads. This is something that is much less predictable. And this required us to implement a solution to basically be able to scale for demand increase. You can see real examples from production. On the left, how CPU looks like when things are not operating smoothly. This is 90% CPU usage, which is not desirable. And here you can see a few weeks when CPU is relatively stable, regardless of the fluctuations in the demand.
So basically overpaid 70% for your hardware.
Yeah, but this is pretty standard. We like our hardware to be used 30%, something like that. 35% is our magic number. If we use it 35%, people are happy. If we use it something like this, that's a catastrophe waiting to happen.
So a real overhead on the budget?
What do you mean by budget?
Hardware budget?
Yeah, I mean, of course. Hardware costs money. It's about $5,000 a node. And of course, there's electricity and all that. So of course, we take it into account. But this product is what makes money to the company. So of course, we want to reduce the footprint of the hardware as much as possible. But on the other hand, if we get more users, then we have all the justification in the world to pay money to be able to serve them, yes.
Are you using any sort of virtualization or containerization to be able to leverage the 70% that's not used when it's not needed?
No. These 70% are used for what I said at the beginning. For example, when we take down a cluster, so utilization goes up in 33% immediately, right? And also, we always take into account overhead for the event that the data center goes into flame. Okay, an emergency situation, and these things happen. For example, I see sometimes it's hilarious. You see these emails because we operate our own data centers, and I'm a client of these data centers. I get this email that a fisherman in Vietnam cut an underwater cable near Vietnam for the metal, and ships are moved to position to fix and we lose the data center because of that. Okay, so it's real. By the way, this guy was executed, no joke, for cutting the cable. Yeah, it's Vietnam. Yeah. Yeah.
Because that's on your conscience?
I followed it afterwards on the news, and this guy, poor guy. But it's nice to see. We get these incident updates, and sometimes you see, dev was pinged, or DevOps were pinged to come and to restart the service or whatever. Not every day you see this email. Ships have been moved into position. The crane has been set up. It's like, yeah, okay.
So it happens as well.
Yeah, execution.
Yeah, tractors, construction don't.
Yeah, the tractors and fiber optics.
Okay, let's begin.
Yeah.
The guys don't get executed. No, but they don't get executed.
Okay, you had a question?
Well, I'm just saying, you're basically saying we're going to 3x over provision in order to make sure that when something happens.
It's not really 3x because, there's some, if you look at the CPU, it's not linear in the way it scales. And, basically when you go 60%, there's hyper-threading going. And so, it's not really 60%, but we definitely take into account overhead. Okay, so therefore, basically, in order to put a bounding factor on the CPU, we need to be able to cap the demand, the number of ads that we basically rank or we spend CPU on each core. And the way we do it is something that is pretty standard in the industry. It's called linear first phase. Basically, we built an approximator model, which is very lightweight. The scores are not very dependent in too many real-time factors. And it's all computed offline. So we compute a set of scores for each ad offline, and we select the score to use on real time based on few user factors. And that's very, very cheap to do because all you need to do is just to sort your ads based on a field. Okay, that's what we do in runtime. And then we take a set of, we can't just select the 20 ads that we want to return. We have to leave margins. So basically, usually we return about 20,000 ads by this approximator. And we hope that the winners, the actual winners by the good model will be within that set. And then only on these 20,000 ads, we run the good model. Okay, the expensive model, the one that is doing all the predictions and conversion prediction and click prediction and all that. And the accuracy of the first phase model dictates the size of the set, right? And as the set gets smaller and smaller, then the CPU usage gets smaller and smaller. If you have a big set, if you return all of your ads in the set, then you basically don't save anything. If you return half of your ads, then you save half of the CPU load by this. Okay? But if the set size is constant, regardless of the size of the demand, then you're pretty much limiting the CPU usage that your host can do. And that's what we've seen in the previous picture. In order to do that, we had to build yet another system. It's called Traffic Monitor, which is using, again, some of the building blocks that we talked about before. And basically, we are able to replay traffic. We talked about it before. So we're replaying traffic into the Traffic Monitor. The Traffic Monitor makes 2 calls to an offline Vespa serving cluster. One of them with first phase enabled, and one of them without. And then we take the score, we take basically both of the results, everything else is constant, and then we take the results and we compare them, right? And when we do it over and over and over and over again, we get statistical significance, and we can actually say if the model is good enough, and we can try multiple models offline, but we can also play with the size of the set that the model is, because basically based on the accuracy to achieve the accuracy that we want. Online, we have to also do it online. The marketplace keeps changing. There's new advertisers, new models launch, seasonality, everything changes all the time. And once you launch this kind of approximation model, you can't just sit idle and enjoy life. You have to keep monitoring it to see that your precision is still as much as you hope it. Because think of it, we basically filter out ads. And if we filter out good ads, winning ads, we're losing money. So the way it works, when the client makes a request, each request is being splitted. The real request goes to the serving cluster, everything we talked about at the beginning, but it's also being teed into a traffic monitor, just like what we said offline, which makes 2 calls, A, B. A is with first phase enabled, and B is without. Of course, this is only for a small fraction of the traffic. And then we basically monitor the accuracy at real time into Yahoo's monitoring and alerting service, which sends us an alert in case the accuracy drops. And the way it looks is something like this, okay? So we look, for example, is top score identical, the actual score by the model. We look at the scores of all the ads. We look at the score diff, and you can see the scale in the score diff, so you can see the precision. And of course, we look at the performance. Sometimes we run a small bucket in production without first phase enabled. And all of these metrics allow us to evaluate and keep evaluating on real time the performance of match phase. Now, the numbers are that by launching match phase, the first version was 97% accurate. And we've recently been able to improve it from 97 to 99%. This 2% of accuracy may seem small, but they yield more than $10 million of annual revenue just by improving it from 97% to 99%. It also allowed us the reduction of at least 800 servers, and we said, with overhead and everything like that. So basically, in production gear, it adds additional something like $6 million just in gear and electricity by the reduction of the gear. So this is pretty significant improvement, and it allowed us to scale the system further. Yes?
The slide before, please. What is the A, the don't care, and the B stands for?
The what, sorry?
Near the arrow, there's A you said is with, B without, and what is the don't care sign, B without?
Right, so basically A and B mean that it's enabled, and don't care means that nothing. And that is not enabled, it's just multiple queries. So we keep getting queries and we have multiple hosts. So basically, again, load balancing between them. Each call is splitted 2 times. That's pretty much it. I can talk about a lot of aspects, but I chose these topics. I hope it's been interesting. I try to talk a little bit about different diversified fields. If anybody has further questions, I'll be happy to answer them now.
What's the speed to you the client receive response from the server?
So I said at the beginning, it's about 80 milliseconds, 99% of the time. Yeah.
How do you generate the load for the stress tests?
How do we generate the load? So each request that we get is basically encoded into a base 64 protobuf with everything, right? The cookie and the IP and everything that we need in order to get a request. And then we log it, right? We log it to Hadoop, we log it to local storage, we have it. And we have a lot of these. And then we have an infrastructure. We have actually two infrastructures that, we have two infrastructure. One of them is local. It's basically a C program that can read them, open a lot of threads as much as we configure to it, and just pushes them either to a remote client or to a local client. And the other option that we do it is end-to-end. So basically we load it to another system, to the gateway where we get the request in the first place, not testing the local hosts, but testing the system end-to-end. And again, it's a similar process where we just open a lot of threads and send it.
How much hardware do you need to generate?
One host usually. It depends how many hosts you want. Remember, our setup is such that each host is one working unit.
So you test every time only one setup?
We can. So usually when we do the launch velocity, for example, we test usually 1 to 2 hosts. Okay, and then we multiply to get the capacity. But many times we do end-to-end testing, and then we take a full cluster and we test it. And when this happens, we usually need a few hosts to generate the load. Yeah.
So you don't use some kind of automation system to generate the load to analyze a load of agents that generate those loads?
No, we have our own.
That means your system is kind of linear. You can multiply.
Yeah. It's nice because it's nice in that sense because it's very predictable, and you take one host out, then you know exactly what capacity you're losing. You don't have any autumn searchers or anything like that.
And you don't get any kind of network limitations?
For this, no, because a lot of the communication is going on between the QRS and searcher, and now they're both on local hosts, so they communicate on local host. Other than that, it's the data center backbone, so they're all sitting on the backbone of the internet. They have a lot of bandwidth. But yeah, there's a lot of network going on.
What do you use for deployment?
Which system? Yeah. We're using, for a launch velocity pipeline, we're using Jenkins, which is wrapped by Screwdriver, which I was saying before that is now open source and you can all take a look. For the actual package management and actual deployment, we're using two technologies built in Yahoo. One of them is called Winst. It's built on top of something very old. You can maybe Google it. It's used to call Inst. And I think it was open source, and Yahoo really extended it. And the second one is Pogo. Again, it's something that I think is proprietary to Yahoo. And it's basically can take a command and distribute it many, many times across all of your hosts. So you give it a host range, and it will basically run a script on all these hosts, and it runs a deployment script. Other questions?
Which databases do you use?
So besides the search engines, which are, you can think about it as a database, we use HBase. And our UI system, which is not managed by us, is using Oracle Enterprise.
Have you considered using some exotic hardware for running regressions or for running models like CUDA or FPGA or something?
For running regression?
For predictive models.
Oh, no. We have.
For example, you can run the predictive models much faster than on a CPU.
Right. So actually, I just had a discussion about someone about it today, maybe using GPUs. But what we did at the end, it's pretty much multiplication of metrics and vectors, right? GPU is very good in it. What we did instead, we worked with the Vespa team in Norway to use machine commands as much as possible to just do it. So, right. So optimize it to this. Can we optimize further on GPUs? Maybe, probably. Is it worth it? Maybe, I don't know. But it's already been heavily optimized, and it's definitely running much faster than it used to.
The training of the classical linear regression has turned out as magnitude improvement.
It's not training. Training is done offline on Hadoop in batch. This is just calculating the actual score in runtime, and it's not linear regression. But that's a completely different discussion. It's a different algorithm. I'm not saying it can't benefit from GPUs, but.
But since you have your data center, you can go.
Yeah, we can do it.
Do very strange things that you can do another.
Yeah, we're thinking about it.
Targeting selecting right ads for right clients, it's when from the what database?
It's all from, you mean where are the rules coming from?
Calculating this, like targeting, scoring.
Yeah. So the advertiser is, when he comes in, he defines a set of rules, right? I want to show my ads only to users who are 20 and older.
Yeah.
So that's a rule. We get it as a rule. And then on runtime, we get all the user data, right? And we get all the ads, and then it's a filter.
Yeah.
So we filter out all the ads that are not matching this user. Simple filter.
But you not estimate kind of revenue from one user to another user just as customers wrote about it?
So targeting is different than estimation, right? The other part of it is basically doing the prediction. Will the user click on this ad or not? So that's a completely different tech talk, this topic. I'll just say that this is separated in targeting, and for that modeling, we definitely learn across users. Like if you're 20 and I don't know, your friend is 20, and your friend click on an ad, and we don't know anything about you, then for sure, I mean, we look at users that are similar to you, that are age 20, that are from the same location, that are speaking the same language, that have the similar interests and all that. And if we know something about the groups that you belong to, then we basically, of course, we deduce to you as well.
By groups, you mean demographics?
Yeah, demographics is one thing. Yeah, interest is another thing. You know, there's multiple factors. Okay, excellent. So thank you very much.